Take it away, JAAMMS or JAAMMS Solar.
All right. Hello, everyone. I would just like to thank you guys for attending this morning. Our company is JAAMMS Solar, and we will present to you our Heliostat design. We are Group 8, which consists of Megan Davis, Matthew Harper, Stefano Marconi, Austin Maxwell, Juliana Mischer, and Alan Osmar. So for our company name, we decided to use the initials of each member, creating JAAMMS. So we decided to also include a company logo, which was created by fellow group member Juliana Mischer. All right, so for the presentation outline, these are going to be some of the topics which we will touch on throughout the presentation. And right now we are going to first start with the Hedgehog concept. So we felt that our group had a very good advantage considering the number of internships, TA positions, and research each member has collectively participated in, putting us in a competitive environment and sharing experience for mechanical design. So our main goal throughout the design was to create a simplistic, efficient design with a minimized cost. We found that efficiency was the most valuable condition because efficiency brings quality and reliability, and to drive efficiency, cost is an important need to consider. So our goal is to maximize efficiency while minimize the cost. Now, to create a simplistic design, we aim to minimize the number of parts necessary for operation, which will ultimately help drive down cost. Now, for the product overview, I will discuss the overall design. The global dimensions are 2.65 by 0.52 by 0.82 meters. The concrete slab alone will have dimensions of 233.9 centimeters by 25 centimeters by 5.08 centimeters. Now for the one single module, there will be 4 heliostats paired with 2 controllers. One controller can power 2 heliostats at the same time. So to eliminate any issues also with shading, a calculated distance of 0.73 meters was determined between each heliostat. And there will also be 1.69 meters distance between each module to also account for the shading, and with a 2,363 modules per field. Now for a more in-depth visual, we provided an overview of a single heliostat. Here you can see how each subsystem, which will also be further discussed later in the presentation, how each subsystem interacts with each other. Now to hold the mirror in place, there are tabs at each side of the mirror with a calculated spacing to allow for thermal expansion, while also providing a foam to eliminate any issues which could arise due to the vibration or shift. And the design also allows for rotation up to 112 degrees in the x-axis and 93.5 degrees in the y. For actuation, we implemented a rim drive, which will utilize expressive controllers to power 2 heliostats at once, since they allow connection to up to 4 motors. And each heliostat will use 2 NEMA 17 DC stepper motors to power the rim drive. The motor which drives the primary axis is mounted on the PVC structure, while the motor that drives the secondary axis is mounted on the primary axis. Now, for the first subsystem of our design, it is the mirror subsystem. It consists of a flat square mirror of 0.5 by 0.5 meters and 4 millimeter thickness. The material is the silvered annealed glass that has a light reflectivity index of 95%. And due to the mirror enclosure tabs, which is part of the actuator system, the total reflective area is 0.246 meters squared. And to also allow for easy maintenance and replacement, one of the tabs will slide out easily so that we can remove the mirror, and then this will further also be covered in the actuator assembly.
All right, so the first analysis that was conducted on the mirror subsystem was the thermal expansion of the mirror under ambient conditions in Nevada. The calculated linear thermal expansion of the glass was 0.55 millimeters. That means that there was a possibility of rattle, but such rattling would introduce unwanted tracking errors to the system. So to make sure that it doesn't happen, we introduced foam to the grips of to account for those expansions and keep the mirror clamped. The next analysis was related to the customer need about conventional cleaning techniques. Most of the conventional heliostat cleaning techniques include either manual wiping of the reflective surface or the pressure washing. A manual repetitive cleaning introduces a possible chance of unintentional scratches that would decrease the reflectivity of the mirror and hence decrease the efficiency of the heliostat. To make sure the mirror surface is protected against such scratches, the arched wear law was used under the worst case scenario, where a heliostat is cleaned manually with an abrasive steel bristle brush. The minimum hardness that the mirror need to have to be able to withstand such wear is about 87 Brinell hardness. Our current mirror has Brinell hardness of 153. The next analysis was on the thermal output of the mirror, since that's one of our customer needs. Thermal output depends on the incident solar radiation, which is the amount of radiation that reaches the Earth's surface. It depends on the amount of solar radiation absorbed, scattered, and reflected by the atmosphere. Local influences of this reduction in radiation can be caused by dust, clouds, pollution, and water vapor. On average, about 70% of solar radiation outside of our atmosphere reaches the surface. Thermal output also depends on the area of the heliostat. In our case, it's 0.246 meters squared. It also depends on the elevation angle of the sun, which is a function of the day of the year, having a higher value during the summer months and lower during the winter. The thermal output depends also on the angle of incidence, which depends on the location of the sun in the sky and the position of the module with respect to the central receiver tower. Reflectivity is the amount of light reflected by the mirror, and in our scenario, we chose the worst case scenario of 82% reflectivity. The minimum power output in the worst case scenario in January 21st was a 423.21 watt per module. The next slide shows you the power output of one module throughout the year, and as seen, it is lowest at the winter months and highest in the summer months. The next analysis was the solar concentration ratio. It depends on the geometric concentration ratio, which was found by total reflective area of 2,363 modules and dividing it by the aperture area, which is assumed to be 1 meter squared. The calculation assumed that the modules are at an angle such that the sum of the elevation angle of the sun and the angle of incidence equal 90 degrees. The thermal output of the sun is on the area of 1 meter squared, which was assumed to be 1,000 watt per meter squared. In that case, our solar concentration ratio is 1,105.29 suns, which satisfies the customer need of having a solar concentration ratio higher than 1,000 suns. Finally, another crucial customer need was to ensure that the collector target tower accounts for dispersion of reflected light from the heliostats. Since light dispersion depends on the refraction index, the distance of the tower, and optical tracking error, and this semester design project did not include design in the field, the only two variables we had control over was the refraction index and optical tracking error. Optical tracking error will be addressed in the actuator assembly later in this presentation, but for the refraction index, we chose the material with the lowest refraction index of 1.37. Their mirror subsystem cost is based on having 9,452 mirrors for the field, which totals to $49,477.76. The cost per reflective area is then $21.26, satisfying the customer needs. And finally, to summarize, the mirror subsystem is able to satisfy all the needs. To capitalize on the small size of their heliostats, we are solving their low manufacturing costs. We are having a high strength and low service and maintenance costs. The mirror size is also smaller than 1 meter squared, and the cost is well below $100 per meter squared, and also $60 per meter squared. The total module area is small in comparison to a non-reflective area, and our module to reflective area ratio is 1.02. Since all parts are off-the-shelf parts, all parts are equal to the cost of off-the-shelf parts. Our surface is washable, and the glass hardness is 153 Brinell hardness, so it's able to withstand all conventional cleaning techniques. The lowest factor of safety for the mirror subsystem was 2.1, satisfying the customer need. The number of heliostats to achieve a 1 megawatt power to the tower was 2,363. And based on that number, the solid concentration ratio is 1,105.29 suns, which is also satisfying the customer need that was bigger than 1,000 suns. Finally, the refractive index is 1.37, which was the lowest refractive index for their annealed silver glass.
The second subsystem of our design is the actuator subsystem. Actuation of the heliostat is provided by a dual rim drive actuated system with 2 stepper motors. All structure for the actuator subsystem, including the gears and the motor housing, are made of PETG and made through injection molding. The prototype of our heliostat would be 3D printed. However, for large scale production, injection molding greatly reduces cost. The mirror is locked in place with 4 tabs on all 4 sides. One of these tabs is removable, which allows for the mirror to slide into place and consequently locks the mirror into its proper location. Lastly, protective housing exists around the motors to create protection from the environment, such as water and dust wearing on the motor. We calculated the torque to determine the sizing of our motor. To calculate the torque needed by the motor on the larger gear, the weight of the motor, mirror support, and wind force alongside their moment arm lengths determined a needed torque of 5.136 Newton meters. To calculate the torque needed by the smaller gear, only the wind force and the weight of the mirror support were part of the calculation, as the smaller gear does not rotate the larger gear's motor, as the larger gear is fixed to the support structure. The torque needed by the smaller gear was determined to be 4.904 Newton meters. To determine the needed torque of the motor, the needed torque to rotate the mirror was divided by the respective gear ratios. The torque needed for the smaller motor was determined to be 0.253 Newton meters, and the torque needed by the larger motor was 0.401 Newton meters. We chose the lowest costing stepper motor that was able to meet our torque needs. This stepper motor has a holding torque of 0.7 Newton meters. Since our design uses gears, one of the contributors to the tracking error is backlash in the gears. Following the book, the gear design simplified. The maximum backlash is 0.04 millimeters. This will result in a 0.0082 degree error. The system also has tracking errors due to the accuracy of the stepper motors. The stepper motors we chose have 200 steps per revolution, which is a 1.8 degree rotation between steps. Our gear ratios are 12.2 to 1 and 20.3 to 1, giving us a tracking accuracy of 0.15 degrees and 0.09 degrees respectively. The total tracking accuracy, which is a combination of error from the backlash and the stepper motors, was determined to be 0.242 degrees, which meets the customer needs. Due to repeating contact stresses, pitting is predicted at the gear teeth. Pitting was calculated by dividing the compressive stress and the endurance strength. The factor of safety for this is 3.65, which is bigger than 2, thus satisfying this customer need.
All right, moving on to the cost for the actuator subsystem, starting with the 8 NEMA 17 stepper motors, as discussed previously, resulting in a cost of $23.99. Next, the injection molded structure. This cost comes from the price of the volume of PETG required, as well as the injection molding process itself, resulting in a cost of $8.37. And then lastly, the stainless steel bolts, sealed ball bearings, and 3D printing brass heat set inserts that we're using, resulting in a cost of $6.42. And then that gives us our overall total cost per module of $38.78. Next, I want to talk about the safety mode that we have incorporated for the actuator subsystem. Although our design is able to withstand the high wind speeds of 94 miles per hour that were stated in the customer needs, our actuator and controller system are not able to accurately track the sun above 45 miles per hour. So in this case, we would be entering a safety mode where the mirrors themselves are turned to be parallel to the ground, minimizing the force of the wind that would be acting on the mirror surface and trying to turn the heliostat. And then going back to the customer needs for the actuator subsystem. In this case, the first customer need has to do with capitalizing on the small size of the heliostat. And for this, we quantified 4 possible issues that could be solved with this. In this case, those issues were manufacturing cost, transportation and installation cost, maintenance cost, and high wind loads. So in this case, all of those issues were solved. Next, minimizing the tracking errors to be below plus or minus 0.25 degrees. That calculation was showed earlier, and we were able to get our tracking errors below 0.24 degrees based on our gear ratios as well as the steps on our stepper motors. Next, to ensure that we were capable of tracking the sun throughout the day, we determined that we had to have a minimum rotation of 90 degrees in both the X and Y axes. In this case, our design ended up having maximum rotation angles of 112 degrees in the X axis and 93 degrees in the Y axis. The next customer need has to do with heliostats and shading. So to accomplish this, we calculated the minimum distance between heliostats to be greater than or equal to 0.73 meters. The next customer need has to do with the heliostats being able to redirect sunlight to a central tower, which we assumed to be 100 meters tall. And that was just a quantity that we used in our initial design. So we do meet that metric as well. The next 2 customer needs have to do with cost. The first one being $100, the next one being $60 per meter squared of reflectivity, of reflective area. And in this case, the actuator subsystem totaled to $38.78, as mentioned previously. So we do meet both of those customer needs as well. And then the next customer need has to do with individual parts being equal to or less expensive than an equivalent OTS part. And due to the complex nature of the actuator subsystem, we did go with a lot of custom 3D printed parts. However, in this case, they are cheaper than the closest available OTS part. So we also meet this customer need as well. And then continuing with customer needs, we had to make sure that there were no open electrical components exposed during cleaning. So like we mentioned previously, we have covers for our motors and gearboxes. So in this case, we did meet this customer need as well for the actuator subsystem. And then once again, having a factor of safety greater than 2. Like we mentioned, we had a factor of safety of 3.65, having to do with the wearing of the PET-G teeth on the rim drive. So we meet this metric as well. Next, the heliostats had to be able to withstand the force created by the high wind speeds. And our lowest yield strength for the actuator subsystem was the PET-G, and in this case, that was 50 megapascals. Next, we have each heliostat must move independently in at least one axis of motion defined by the customer. And in this case, we had both axes independent motion in the X and Y. And then last, we had to ensure that the operational temperature was greater than or equal to 117 degrees Fahrenheit based on the temperature seen in the environment in which we are in Nevada. And in this case, the lowest maximum temperature for our components was 176 degrees Fahrenheit, and that is once again based off of the PET-G material being used.
Moving on to our controller subsystem, our controller setup consists of the following components: an expressive ESP32 controller and an A4988 stepper motor driver, all enclosed within a PET-G Lure V ventilator box. The enclosure was assigned and fastened vertically in order to provide the necessary passive natural convection and ventilation. Silicon-coated 19-gauge copper wires with waterproof connectors are used to protect and run all wiring from our controller enclosures to our actuator subsystems. The 19-gauge wires were specified for the system based on the current experience, and the wires entered through the bottom surface of our controller enclosure box. For first analysis for the subsystem in the form of natural convection. So in our current dimensions of 175 millimeters for our height and millimeters for the length of the control box, natural convection by itself will not occur. This is because the ratio of our height to our length of the box is not greater than the 4th root of the Rayleigh number that we calculated, indicating that natural convection will not occur. For this reason, a set of Lure vents were implemented along both lids of our controller box. The ambient temperature in the enclosure was solved for on the following conditions to determine whether the quantity and total area of our implemented Lure vents provided a temperature that our specific controller could operate in. The absorbivity and reflectivity variables that you see on the screen were taken off the material of our enclosure box, which in this case was PETG. Solving for this, we achieved an ambient temperature of 64.8 degrees Celsius, which is well below the operational temperature of our expressive controller, which is 125 degrees Celsius. Regards to our thermal analysis, to obtain the required thickness of the enclosure box for our controller, a thermal circuit analysis was implemented on the assumptions that area was constant throughout and that the only net was active. Under the following circumstances, a thickness of 0.0145 meters was arrived at for all controller enclosures. And this includes the thickness of the flanges of the controller as well as both sides of the lids. Finally, with regards to cost, the total quantity of controller enclosures and expressive controllers was calculated to be 4,726, resulting in a total cost of $11,176.09 and $8,321 respectively. Adding these values and then dividing by the product of the total number of modules times the surface areas of each module results in a per meter square value of $14.11. Referring back to our needs, the total cost per meter squared, as stated earlier, of our controller subsystem is $12 per meter squared and $60 per meter squared. Our expressive controller is able to operate at a Wi-Fi frequency of 2.4 gigahertz and with the customer need interval between 1 gigahertz and 5 gigahertz. The expressive controller is also able to implement on all three automation features, which include sending signals to specific motors, being able to move motors in 2 axes, and also using readily available software. Our PETG enclosure also allows for all electrical components to be shielded from washable surfaces, therefore keeping the number of electrical components near washable surfaces to be 0. And the operational temperature of our controller is well beyond the required operational temperature for the zone we are trying to operate in.
As for the final subsystem of our design, this is the structure subsystem, and it is composed of the following components. For the base, it is a narrow concrete slab with dimensions of 0.25 meters by 2.339 meters and is 2 inches thick. This thickness was based on the minimum depth for the Tapcon screws. Connected to this concrete base is an injection molded base flange that will be secured with 4 Tapcon screws with washers that distribute the force across the top base. A PVC pipe is used as a central supporting column, and to attach this PVC to the base flange, polyurethane glue is used. Polyurethane glue is also used to attach the injection molded pivot cap to the top of the PVC pipe. Even though the pipe should be shaded most of the operational time, the PVC pipe will be painted to provide additional protection against UV light. As for the operational temperature, this system has an upper threshold of 160 degrees Fahrenheit. For the first analysis, the wind force and lift force was calculated. The wind force was calculated by multiplying the wind pressure caused by record high wind speeds and multiplying that by the reflective area of the heliostat. This value is then multiplied by the lift coefficient and the sine of the angle of the surface with respect to the horizontal. This brings the value of the lift force to 433.7 newtons. As for the adhesive shear strength of the polyurethane glue, this requirement of the part is the shear strength of the adhesive, and it must be greater than the shear stress experienced due to the lift force. The shear area is the interface of the base flange, and the shear stress corresponding to this is 0.0948 megapascals. The allowable stress is 2.2 megapascals, and this shows that the adhesive will not fail under the lift force due to the factor of safety being much greater than the customer requirement of 2. As for the factor of safety for the Tapcon screws, this is found by multiplying the rated pull-out force of 1 screw by the amount used to secure the base flange. 4 screws are used, each with a rating of 667 newtons. This brings the maximum pull-out force to 2,668 newtons. Dividing this by the lift force gives a factor of safety of 6.15, which is above the customer requirement of 2. As for the flange, this section is in regard to the factor of safety of the injection molded base flange. The stress was calculated by dividing the lift force over the top face of the base flange, which results in a stress of 0.24 megapascals. Since the yield stress is 28.3 megapascals, this brings the factor of safety well above the customer requirement of 2. On to the cost. To calculate it, the amount of concrete needed had to be determined, which came out to 1,382.3 square meters of 2-inch thick concrete slabs. The total cost for the concrete for the entire field is $30,127.20. And for one module, the cost is $12.75. This subsystem also takes advantage of injection molded parts that have a cost of $2.52 for the entire module. The amount of PVC pipes used for the entire field is 9,452. And this comes to a total cost of $4,780.80. For one module, the cost of PVC is $2.03. Overall, the entire subsystem comes to a cost of $27.78 per square meter. As for the customer needs, it addresses them through these following design specifications. For the first customer need of the structure accommodating 4 to 16 heliostats per module, our design has 4 heliostats per module. As for the cost, the total cost of our design of the structure subsystem is $27.78 per square meter, which is well below the $100 and $60 per square meter. As for the total module area being small, the ratio between the entire structure to the reflective ratio is 1.02. For the OTS parts, the necessary parts are OTS, and when possible, injection molded parts were used to minimize the overall cost. For the factor of safety being greater than 2, the minimum factor of safety of this subsystem is much greater than the customer requirement of 2. As for the lift force, through our analyses, all components were able to satisfy this force requirement based on their corresponding stress and the yield stress of the material in question. And for the operational temperature, our structure subsystem has a threshold of 160 degrees Fahrenheit.
Moving on, we want to talk about some of the key features of our design, starting with our short field assembly time of about 30 minutes that we are able to achieve by minimizing the total number of fasteners, using threaded inserts to reduce tooling required, as well as reducing the overall number of parts that had to be assembled together. Next, we want to talk about our gear covers that have strip brushes to prevent dust and sand getting between moving components. Next, I want to talk about the gear covers that we're using to prevent dust and sand getting between moving components. We have strip brushes attached to those covers, which wipe off the rim drive gears before they have to interact with the motor. That kind of leads into our next point, which is that we are able to withstand all conventional cleaning techniques. Our controller box is enclosed, our motors are enclosed, and our fasteners are made of stainless steel, our bearings are sealed, and our threaded inserts are made of brass. All of these things help waterproof our design so that we are able to use power washing or manual scrubbing for cleaning techniques as mentioned previously. This waterproofing also leads into our last key feature, which is resistance to high weathering conditions. As mentioned, the covers prevent water and dust from getting into our components. And then we made sure that our modules were able to withstand the high wind speeds of 94 miles an hour that are sometimes seen in Nevada. Moving on to the cost summary for the entire field, starting with OTS parts costing around $510,000 and making up 50% of the total cost, shipping costing around $26,000 and making up 7% of the cost, assembly labor costing $92,000 and making up 24% of the cost, and lastly, manufacturing and manufacturing labor of around $173,000, making up the last 19%. Resulting in a total cost of $801,000 and a total cost per module of $339. Also, the energy per field required is about 51 cents an hour, and we've included a monthly cleaning fee of $12,000 to account for power washing the Heliostat modules. Next, we want to talk about why we think our design should be prototyped. As we've talked about, there are minimal manufacturing methods required, mainly 3D printing / injection molding, drilling and cutting PVC, and pouring concrete slabs. We've used readily available OTS parts primarily.
Minutes per mile, split pace, 6 minutes, 13.
We've tried to utilize readily available OTS parts, and the modifications that are required for those, we have also tried to minimize, such as simply drilling PVC pipe. We've also used 1.69 meter spacing between the rows to eliminate shading, and it has also enabled us to use 4x4 utility vehicles to simplify cleaning, maintenance, and service to the Heliostat modules. Lastly, our modules are able to be individually controlled using the expressive ESP32s that we've talked about previously for the controller subsystem. In conclusion, our design is robust, efficient, and reliable. And we capitalize on the innovation of a heliostat with a small form factor to harness the abundant energy provided by the sun. We wanted to thank all of our sponsors, and we really appreciate your time for attending our presentation. Lastly, we do have an appendix with further calculations if that is something that anyone else would like to see.
All right, I would like to encourage our external visitors to go first. So Julia, you're up.
Hi, friends. First, great presentation. Y'all did a really good job. And let me apologize in advance. I have a puppy on my lap that is 3 weeks old and is trying to eat everything at the moment. So I have to hold her at the moment. If you would go back to your cost slides, please. Perfect. Let me just start off with thank you so much with including assembly and manufacturing labor costs. You have no idea how many times I harp on this with other groups because they don't. And as you can see here, it's a pretty significant number. It's a large part of your costs. So I actually feel fairly confident. A lot of times I'm getting people that if they do calculate it, it's like, oh, it's like 1% of our costs. And I'm like, no. So I actually feel very, very confident that y'all did your costs the correct way with the assembly and manufacturing. So I really, really do appreciate that. Now, the other thing the total price per module is $339.24. Is your module 1 square meter? How does that relate to the customer need?
As I can explain that, our module is a little bit smaller than 1 meter squared. It is 0.986 as far as I remember. So unfortunately, we're not meeting that customer need. However, that is justified with the current problems with their supply chain and their very fluctuating prices, as well as high manufacturing labor costs and assembly labor, as you've mentioned before.
Okay. So I will say the very first thing as an investor, I say I need it at, and we're just going to go with your thing is 1 square meter because I'm not an engineer and math doesn't work well with me. So since it's so close to 1, we're going to do 1. You're coming at me with, oh gosh, excuse me. You're coming at me with over 3 times the price. So that's very scary. I would say, start looking around. You've got to figure out ways to reduce that cost. Believe me, I know that materials right now have skyrocketed. Believe me, I know that. I was looking at building a house, and let me tell you how much I did not do that because of the price of everything right now. So, maybe when you start off, when you do talk about the costs, that may be something to mention, hey, look, we know we didn't hit the target. Right now, the cost of wood and steel and this, that, and every other thing is, outrageous. We are predicting, and then do some research. Is it predicted that these costs are going to go down? Is it predicted wood's going to go down in the next 1 month, 2 months, 3 months? Or is it going to stay up? So, because the thing is, if you come to me with, $339, I'm going to come back with you with, sorry, I have $100 per meter. I may have a little wiggle room. I may be able to go to my boss and say, okay, well, I need like $120 per meter. But usually the person that you're presenting this to is getting a lot of their constraints from someone above them. So wiggle room, yes. Over 3 times the amount, not so much. Okay, left field from that. I cannot thank you guys enough for all looking professional. All of you are dressed nicely. You have the same background. You're all sitting up straight. You're talking clearly. I'm obviously not acting professional with a dog in my lap. But for someone like me who's an investor, when it looks like y'all have your act together, I very much more believe that you do have your act together, you know. So and you know what, that's all perspective. You may actually in the background be like, I have no idea what I'm doing and I'm faking till I make it, you know. But if you give off that perception, and again, by the smallest things, dressing up, looking nicely, sitting up, speaking clear, having the same background, when you look like you have your act together, you'd actually be surprised how much more you start getting your act together, you know, just by looking and feeling it. So kudos, like A+++. You give me confidence in your heliostat, even though I literally understand none of the engineering parts behind it, a lot, because you are presenting yourselves like you know what you're talking about. So thank you very much for that. And I will be quiet now.
Thank you for your feedback. And yes, we will look into the cost more.
Yeah, thank you so much for coming. Unfortunately, I don't see any other external members, so I will go ahead and go next. And yay, we have Trom with us now in full living color, full participant, so he may have a bit to say too. First of all, I like when you went over the customer needs for each of your subsystems, that you included cost. As opposed to leaving it towards the end and then surprise. I would like to see, instead of having it as like $100 for each of the subsystems, it's sensible to go ahead and budget it like so much percent for this subsystem where, you know, all the percents add up to 100. That would sort of leave more sense as we're going through, and then it'd be like less of a surprise that when you total everything up, you don't meet the need. I have a question about the controller box that protects everything. So you have vents in the back, and oh good, you're gonna flip to a view of that. So I would call that the back side, and I see at the bottom a few vents. What does it look like on the other side? Are there any other vents other than the 3 on the bottom in the back?
Yes, so they're actually, when you see the 3, the same configuration on the back that shows they're at the top, towards the top of the controller box. So they're kind of inverted. You could think of it that way.
Okay, so you actually planned it for natural convection where the hot air rises and has a place to leave and the cooler air. Good job. Okay, so that makes me happy. And thank you very much for considering backlash in your error analysis and not just assuming you're going to be able to control it to the resolution of your motors. Oh, your thermal analysis, did it include heat generated by your electrical components? Did I miss that? Or was it just heat from the sun beaming in on the box?
I think I can answer that. So in the slides, we did not include that here. However, we did calculate we did perform a thermal analysis, including their generation temperature, and we are still meeting this 64.8 degrees Celsius.
Okay, good, because I think, you know, that's going to be a significant percentage of the heat you have to deal with, and it just was not clear to me. And last but not least, so your concrete base is 2 inches thick, and it's very long, but it's not very wide. So imagine you have your 4 heliostats on that, and they're all pointed, elevation about 45 degrees, but they're all pointed perpendicular to that concrete pad. And we get a wind blowing on it. What is the slip or tip? You know, it's, you know, how high is that? You know, is it gonna, it looks like it wouldn't take much of a wind to knock it over. Have you calculated, how much wind it can withstand in that position before it just tips the whole concrete pad over?
I can answer this. I'm not sure we have a calculation for the exact scenario that you've described. However, we did do a worst case scenario using the volume of the concrete and finding out the weight and determining how much wind it can withstand before it is lifted or slid over the ground.
Did that include the moment arm?
I believe so.
Okay, and how much wind would that be?
I'm not sure we did it as a factor of how much wind, as much as we used the 94 miles an hour and came up with a factor of safety that we made sure was greater than 2.
So, it just kind of seems that, in this direction with any sort of lever arm there, it wouldn't take much to tip it over, but thank you for, would that be in your appendix slides? Because let me see. So thank you for having slides that you thought, no, maybe they don't just quite fit in, but maybe they'll have questions about that and including it, because that's a very good idea. Pull out. So what is your force pull out? I see substructure subsystem factor of safety for pull out.
Yes, I can answer that.
What's getting pulled out?
The pullout is the rating for the concrete screws. That's just how much force it can experience, I guess, normal to the surface that it's attached to before they pull out of the concrete.
But you don't have the tip calculation. Okay. Love the bit about the birds. All right. And with that, I will pass the mic on.
Would you like me to speak more about the birds?
Not necessary, but if Trom has any questions, I'd like to let him go. And thank you so much for coming, Julia. We really appreciate it.
Thank you, Dr. Chesney.
Okay, so I guess it's my turn. So sorry, I've been kind of MIA. I have to do a infusion every 6 weeks to keep a medical condition in remission. So that's where I was. So sorry to kind of pop in here at the last moment, but I did listen to the whole talk while I was making my way back from the hospital. I mean, I don't know how to say this any other way. You guys basically broke my class. So like, I really don't have any issues with any of the technical stuff, but I'm going to tell you just a little war story and then ask you a question. So when I was about to graduate with my PhD, and there's no industry people here, so I'm going to make fun of industry people too. I interviewed with GE, General Electric.
I'm still recording. Should I stop recording?
No, that's okay.
Okay.
GE needs to hear this because they missed out on hiring me for this reason. So I interviewed with those guys in their research division, and I hadn't finished my written dissertation yet, or my defense, and my expectation was to basically get a job offer and have 3 or 4 months. And they interviewed me, and when the interview was over, the hiring manager pulled me aside and he's like, we're going to give you a job offer, but you need to be available in 2 weeks. And I said, well, you're then going to get Matrom MS and not Matrom PhD, and you're never going to get Matrom PhD because I can't finish my PhD in 2 weeks. And then he said, well, if you can't finish your PhD in 2 weeks, we're not going to hire you. That's what we at GE call a stretch goal. And so they sort of laid it out like that. So I'm gonna pose a stretch goal to you guys. By the way, I didn't take the job, obviously, and went into academia instead. So for this design to have any realistic chance of propagating forward, and by no fault of you guys, it's just bad timing. We need a functional prototype in 3 weeks, so that we can inject it into the summer Mech 3 course. So if I came up with, I think you guys had a per unit cost of it was something like $300 or $400. I realize that's for mass scale, but if we were to come up with $500, could you guys build this for us in 3 weeks so that we can use it in summer? That's a stretch goal, but
We probably could. We might have to scale down some of the things as the size, like if we're using the printers in lab, it wouldn't fit on those printers.
the whole thing wouldn't fit. But could you build one unit, like not the whole thing, but just one of the mirror units?
Right. I'm saying there's parts of our actuator that don't fit on the Prusa printer beds, but we could scale the whole thing down possibly.
I hate to volunteer Dr. Chesney's printer, but I hear Dr. Chesney has a bigger printer.
I do, and there are other, it might be fun for me to do, but there are other printers that would be available in other labs, I think, that are, more legit. I mean, we have the whole new engineering building has huge, wonderful printers. And I don't know who gets to use them.
Nobody at this point.
And
I think
since
it's also the Thermalab does that. Thermalab is using a big printers that could possibly be volunteers / asked if we could use them too.
yeah, and since it's quasi multidisciplinary, across several teams, it's not just for teaching students, but it's also for solar research and whatnot. It seems like a good candidate to ask around.
Yeah. So I don't want you guys to commit to this now, and I hate to ruin the first couple of weeks of your summer. I'm sure you guys have internships and other things lined up, and you don't want to spend the next 3 weeks working 18 hours a day getting one of these things built. But and we can talk about this when we're not recording anymore offline potentially. But I would really like to have this design in the summer class so that